All right, so let's have a go now at drawing our probability distribution histogram and our cumulative probability distribution histogram. We'll do the histograms first. Now for this one, I just need to get my scale on the y-axis to go up to 6/16, which I've labelled as 3/8, so it's a bit simpler. And because I know I've got 16ths, I've just put some notches in between the 8ths to take care of those. Now I've labelled the y-axis the probability that x equals any one of these values of x. So I've got 1, 2, 3 and 4 going along the x-axis, but you'll notice I've put some notches in between my data points, and that's because I want the top of each column to be centred around the actual number. So when I go to graph 1/16 for 0, I want the top of the middle of my column to be right above the 0. So that means it has to come across like this, and curiously it actually has to come across to the other side too. And it looks a little bit strange to go onto the left side of the vertical axis like that, but that's just how it's done. Now for 1 I need 4/16, which is 1/4 or 2/8, so that needs to come up to this sort of height. And you can see I can build my columns from each of those in between notches. Then I've got my next one's the tall one, goes all the way up. Now I'm just doing mine roughly without a ruler, but you get the idea. You can make this a little bit neater. And the bottom one's 1/16 again, and will extend out to that 4.5 point. So that's the probability distribution histogram. Now when I go to make the polygon needs to join the most important part of the histogram. So in this case, we're looking at the probability of x being equal to some value. We want it to line up with the centre of the column, because that's what this graph is all about. Now if I go ahead and join those up with straight lines, well, that wasn't very straight, was it? But you get the idea. That was a bit dodgy. Okay, straight lines here. I'm nearly done, but it makes the most sense to actually ground this polygon all the way down to the x-axis. And there's a good reason for that, which I'll explain in a moment. Now, when it hits the ground, it also makes sense to hit the ground exactly 1 unit across from the lowest data point or from the highest data point. So over here, where notionally I've got 5 and -1, that's where it's landed. Now, the points on this polygon say the probability of x being any particular value of x. So it makes sense that there is 0 chance of getting -1 heads when I toss a coin 4 times, and there's 0 chance of getting 5 heads. So that makes logical sense to bring it all the way down to where it's an impossibility. All right, so that is our probability distribution histogram and our probability distribution polygon. But we've got a name for the polygon. It looks like a function, doesn't it? And it passes the function test. A vertical line would only come through it once. So we call it a probability distribution function. So you can write that down underneath it if you like, probability distribution function. And the function is actually the polygon part. Okay. Now, we're going to make PDFs and CDFs with our continuous data, and that's the place we do it more often. But I think it makes most sense to start with discrete data because they're really easy to draw, and then we can understand a really important concept. Now, the important concept that we're going to understand when we work with continuous data is that if we know the area underneath our PDF, then we know something about the probabilities. So you'll notice something interesting here. We know that if we add these numbers up together, we get 1. So if each column is 1 unit wide, then I've got 1/16 area here in this column, because it's 1 times 1/16. I've got 1 times 4/16 in area here, or 4/16. I've got 1 times each one of these. So the area of these columns actually does add up to 1, doesn't it? But what you'll see also is the way that the polygon gets drawn. This little triangle here is exactly the same size as this one, even though mine's a bit dodgy, doesn't look perfect. And this one is the same size as this one. They're the same size as each other. This one and this one are the same. This one and this one. This one and this one. And this one and this one. So they're all in little pairs. So what we actually find then is that the area under the PDF which is the polygon, equals 1. Now that's an important concept we're going to need when we look at our continuous data. And of course, continuous data is going to have an infinite number of columns. So in fact, we can't draw a proper histogram with continuous data, can we? But we can draw the polygon. And what we find is that it ends up with a bunch of dots that are so close together, it makes a smooth line or a function. And that concept that the area underneath the PDF equals 1 is how we're going to look at our probabilities once the data is continuous. All right, so looking at our cumulative data now, we can graph this as well. On our y-axis, we're going to need to go all the way up to 1. So let's have 1 there. We'll need 16ths. Let's go 8 16ths here, 12 16ths there, 4 16ths here. So we're working in 16ths, and then I can just halve each of those to put my things in. Now, just as with this histogram, this one needs to extend so that each column sits above its number. So my 1/16 needs to look just like this. That's 2 16ths, so it's actually going to look a lot smaller because my scale is different. That looks like a really tiny column. Now I need 5 16ths, which is going to be here. Now I'm sort of drawing this by bending over and looking on the side, so it's a little bit dodgy looking. 11 16ths is going to be up here, something like that. Again, the lack of a ruler is making mine look a little bit less than perfect. 15 16ths will be up there somewhere, almost at the top. And then 16 16ths is now a certainty, because remember, it's a certainty that when I toss 4 coins, I'm going to get 4 heads or less. So quite easy to build the histogram, no harder than this one, but here's the thing to remember: when we join the columns together here with a polygon, we've got to join the most important parts. Here is the center of the column, but here it's the top right-hand box of each column that needs to be joined. And the reasoning here is that if you take this top right-hand corner and say the chances of getting 4 heads or less is this, it corresponds really nicely with that 100% certainty. And we start there as our starting point, because if you started here, it can be confusing. Hang on, is this part of the 4 box or the 3 box? So it's just convention that we do it this way. We join the top right-hand corner of each of our columns like that. And if we do it that way, you very naturally end up with your polygon being grounded, if you like, down on the bottom left corner of your smallest column. Now, we can say here that each of these columns represents the chance of getting 4 heads or less, 3 heads or less, 2 heads or less, 1 head or less, 0 heads or less. And when we're looking at one of these histograms, you need to use that or less over and over to remind yourself what it means. And on the y-axis, we can see it's the probability of the outcome being equal to or less than any of these given values. And just as we call this one a PDF, a probability distribution function, our polygon here has a special name. We call it a cumulative probability distribution function. We don't put the P in for the probability, just a CDF.